Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Yeah, we do. I am Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and aspiring friend to the universe.
Oh, I love that. I'm Corinne. I am a comedian, a writer, also a friend to the universe.
Yeah, you are.
Hopefully, if they'll have me.
I'm going to say yes. As someone who has channeled the galaxy, which is not the whole universe, I'm going to say yes. You're at least on the galaxy's good side.
I'm on the galaxy's good side. Okay, good. I don't want to get on the universe's bad side.
So, Corinne, I'm so happy about where we're recording today.
Yes, me too. Tell me about it.
Yes. So it is a little loud. We have had to find a quiet corner of this local carnival that we are visiting. There are lots of games. You know, I see someone over there right now absolutely failing at the strongman game, which brings me much joy.
That is so rigged.
There are small rides all around us. I hear the children screaming. I hope it's in joy. And there is so much delicious food around at the end of this, Corinne. I'm going to eat like 5 corn dogs.
I know. I did clock a fried pickles thing when we came in. And I was like, I gotta get there.
Hell yeah. But before we can eat the fried pickles and the corn dogs and the funnel cakes and all of the other delicious carnival food, we are here to talk about actually one of my favorite classes from grad school.
I'm excited to learn about this because my gut instinct is bad. I don't think this is for me. So I'm really curious. I need it to be explained to me by someone who's excited.
But that's how you felt about the Big Bang, too.
That's true. That is true.
Mm-hmm. So by the end of this, you'll be a lot more comfortable with fluid dynamics, which is the class.
Amazing.
So I have kind of always wanted to be famous enough that I could eventually sell my notebooks, or so that my surviving descendants could sell my notebooks for money. Like, that's the level of fame I want to reach.
Okay, I did read, this is not science, but I did read Sylvia Plath's, unabridged journals, when those are published, and that was, the coolest thing ever. So I totally get it.
So I wanted to kind of kickstart that process by going through my notes from college and my PhD program and sharing some interesting tidbits from those notes with you. So if you are one of our patrons, you can join at patreon.com/palebluepod. You can get scanned copies of my notes from grad school that we're talking about today.
That's so fun.
I will tell you now, I looked at those notes and I was like, what the fuck do these symbols mean?
Were you a doodler or were you a very focused note taker? Because I was always in the margins doing something.
Oh, that's cute. No, I was a very focused note taker. My notes were color-coded so that equations were in one color, figures and graphs were in another, notes were in one color, and questions that I had about those notes were in a different color.
That's a great idea. And is this highlighted or you're switching colors of your pen as
Just switching pen colors. Wow. Yeah, I got those multicolored pen packs.
Those are great. I definitely always had a burst of that at the beginning of a semester where I was like, this is the year or the course where I'm going to be the ideal student. And quickly was like, I actually can't pay attention.
I've been there. I had classes where I really did not want to pay attention. But once I got to grad school, I was like, oh no, I need to pay attention.
Yeah, now I really picked it myself and I need to.
Not only did I opt into this program, this is how I make money.
Yeah, this is the rest of my life. Okay, so this course is called Fluid Dynamics, but what other classes did you take in school?
Just in grad school, the classes I remember taking, and I think this is in rough order of least liked to most liked. Let's just start off being chaotic now. So I had to take a class in stellar processes, so what's going on inside of stars. That was at 8:30 a.m. every weekday. I've sat in the front row of that class and fell asleep almost every day. It was awful.
Oh my! I had an 8:30 a.m. class in undergrad for, I went to school to be an elementary school teacher, and this course was for math, learning how to teach math to kids, kind of. But it was at 8:30 in the morning. I was commuting from Staten Island to the Upper East Side. So I was like, this is set up for failure. And then I'd be like, oh, but it's no big deal because it's elementary math. The teacher I had 2 semesters in a row, she called me Connie.
Oh, that's not your name.
For 2 semesters in a row. No, and I was like, I actually can't correct her now because we're too deep into this relationship. Right. So not only am I late, tired, exhausted, but she doesn't even know who I am.
Well, maybe she didn't count you as late.
Yeah, that's what I'm hoping. I had a gym teacher like that in high school.
So that was stellar processes, which I'm pretty sure was my least favorite grad school class. I also took a class in radiative processes, which is like after radiation is outside of the star, where does it go and how does it behave just like in space? I took one, I guess, elective course on climate systems to bring it back home to Earth.
Okay.
I took a class on the interstellar medium, which is the space between stars. And that was such a joke class because
Really?
the professor was so easygoing. I don't think I learned anything of substance about the ISM, but I did see that professor do so many times. I saw that professor do a remarkable impersonation of a ferret. Because he had a pet ferret.
That's so funny. That's so funny.
So that was the interstellar medium. I took a class in cosmology, which actually wasn't terrible. I took a class on galaxy dynamics and evolution, which I liked because it was just very relevant to my research. And finally, fluid dynamics.
Here we are. That brings us back. So why did you like fluid dynamics?
Part of it was just that I had a good teacher for it.
That'll make all the difference.
It really does. By the time you get to grad school, the people teaching those courses are researchers. They did not go to school to teach. They didn't go to school to learn how people learn. They went to school to study science, and now they teach science. So you have a huge range in grad school of professors who actually care about teaching, and this professor did. So I had a good teacher. The homework was relatively fun. It still made me cry. I still had to do a lot of equations and derivations of stuff, but it was relatively fun because it talked about practical stuff. Like I remember we had this one homework problem where we looked at a traffic jam and studied that as if it were a fluid moving like along the road. Ooh. So that was really fun. And I just love that fluid dynamics has more practical applications than any other class I took in grad school because we deal with fluids all the time here on Earth. Those fluids move a lot. So if you've ever been in traffic or mixed a drink or if you've flown in an airplane or if you've experienced weather, and I'm pretty sure everyone here has experienced weather.
I'm experiencing it right now.
Right, yes, in this moment. Yeah, we're outside at this carnival.
Yeah.
We're experiencing weather. That is all fluid dynamics.
Interesting. Okay, because I was going to ask, I feel like some space words might, like fluid, but it's actually no fluid I've ever interacted with or like have understood. So I was curious how much this was like the fluids I know well.
Yeah, all of it.
So what is a fluid, I guess? Or how is it defined?
Yeah. Fluid is like a catch-all term. It is not one of the states of matter. So the four states of matter that people might be familiar with are solid, liquid, gas, and plasma. That's the fun bonus fourth state of matter.
Did plasma join the scene later in life? In my life, because I feel like when we were in school, in elementary school, it was like three. There are three, and it's like all the things water can do.
Yes. Yeah, it did get added later. That's like high school level chemistry and physics where they're like, oh, and
by
there's
the way,
this
there's
fourth
plasma.
one called
Yeah.
plasma. Yes. Plasma is just like a mass of charged stuff. Like electrically charged particles make up plasma.
Okay.
So we don't see a lot of plasmas here on Earth, but we do see a lot of plasmas in space. Like stars are basically plasma.
Of course.
So let's focus on the three states of matter that aren't plasma. There's solid, which has a set volume and a set shape. So if you have a solid object, you can't make it take up less space, and you can't change its shape, with some exceptions, you know.
Right.
Then liquid has a set volume, so it takes up the same amount of space, but it doesn't have a set shape, so it can move. It's very, trying not to use the word fluid here, but it's very amorphous. And then gas has an unset volume and an unset shape, so you can change the amount of space it takes up, and it can be in any shape it wants. And a fluid is anything belonging to any of these states of matter that flows, usually a liquid or gas.
Okay, that kind of makes sense.
Yeah.
I quickly will say one of my favorite TV shows lasted one season. It was on like MSNBC, which is such a strange place for a reality show.
Huh.
It was called Staten Island Hustle. And it was these absolute bizarro guys who would meet once a week in the top floor of this restaurant called Angelina's. And they would pitch ideas to each other. It was kind of like a Shark Tank.
But Staten Island.
But Staten Island, exactly. So they would pitch business ideas to each other, and they would all go around and be like, well, I can give you $1,000 for that, or I can give you $5,000 for that. There was one idea for 3D salad dressing.
What? What?
And this is...
It's already in 3 dimensions.
Thank you, yes. Okay, so you get it. Obviously, our scientist gets it. But he was like, guys, this is the first 3D salad dressing. Look at this. And he poured regular, like, balsamic dressing onto a plate. He was like, look how flat it is. And in my head, watching this, I'm like, well, liquid takes the space of the container it's in. So, of course, it's going to, like, go flat. So then he pours out his 3D salad dressing. And it's like a mound on this plate of feta cheese and tomatoes. And, of course, it's, quote, 3D because it's a pile of cheese and vegetables.
That's not dressing.
No. So then he did like a taste test at the local grocery store, which is a grocery store my parents shop at. So I was especially excited. Everybody was like so confused about the 3D salad dressing part, like every customer. And he was getting so frustrated. He was like, it's the world's first 3D salad dressing.
He just made another salad.
He made something up.
Salad.
Fully made it up. It's just a piece. Anything you experience, I feel, is 3D. Like anything you're gonna put in that salad is 3D.
3D salad dressing. I hate that so much.
Anyway, I'm hoping he listens to this.
Me too.
Okay, so anyway, so fluid, it's moving, it flows. What is making it flow?
Yes, there are lots of things that can make a fluid flow, that can make a gas or a liquid move around. One of them is gravity or any sort of propulsive force. Also, wind, convection. I will explain more about what convection is later, but that depends on differences in temperature, density, and pressure within a substance. And magnetism, any sort of magnetic energy, can also make fluids move. This is not an exhaustive list, but this is the list of stuff that is relevant to what we will talk about in this episode.
Okay, noted.
I cannot take an hour to describe all of fluid dynamics. I had to take a whole class for a semester about it. But there are some things that I feel like you might want to know about fluid dynamics. Some terms, some equations that you might want to just like say you've heard before. Maybe some of them you have heard before. Let's see. One cool concept or idea in fluid dynamics is the difference between laminar and turbulent flow. I know you've heard the word turbulence before.
I have heard turbulence.
Have you heard laminar?
I don't think so.
Yeah, it's a lesser known word. So there are two types of flow, laminar and turbulent. Laminar flow is very streamlined. It happens when particles in a substance are flowing in parallel without mixing. So think of water flowing perfectly out of a hose. If you've ever seen a video of a water stream where it doesn't look like the water is moving.
And then people run their hand over it. Yes, I've seen YouTube compilations of that.
That is laminar flow. The reason it looks like it's not moving is because when our eyes register something as motion, it's because like something is changing in our field of view. But for laminar flow, because there's no mixing visible, nothing appears to be changing.
Interesting.
So it just looks like a straight line.
Our eyes are weird.
They really are.
I don't think we can trust them.
We probably shouldn't.
Yeah.
Turbulent flow, on the other hand, is when the particles are mixing together as the substance is moving. So this can be caused by an external obstacle. So picture a river flowing. Any sort of rock in that riverbed is going to cause a turbulent flow. Or any internal inconsistencies in the fluid, like if it's a mixture of different substances and one of them is more dense than the other, or even if it's the same substance, like two instances of the same substance, but you're pouring like beer out of two different mugs into something. One mug of beer might be higher up than the other, so their velocity would be different, and then you'd get this turbulent flow. There are lots of things that can produce turbulence.
Yeah, I was going to say, I feel like turbulent flow I mean, I don't know if it's more common, but it's certainly something it seems like I've experienced way more of than laminar.
Yeah, absolutely. I know you have experienced turbulent flow because you have been on a plane, Corinne.
It's true, I have.
Imagine if you hadn't. If I'd came in all confident, you've been on a plane.
The big reveal. I actually travel by foot everywhere. That's just
everywhere,
me.
Even across the ocean.
Yeah,
So airplanes work because of turbulence, because of a difference in air velocity in different places around the airplane wing, which is what lifts the airplane up. So I want to just take a quick break from space right now to explain how airplanes work.
Oh my God, I'm so glad you are because, okay, I used to teach at the Space Center in New York, and one of the classes was on planes for third graders, and it was one thing I always had a hard time getting my head around. I'd always need a refresher 5 minutes before I was about to teach the class to be are you sure I have this right?
Yeah, it still feels like magic. Every time I get on a plane, I'm the sorcerer's keeping me up now.
Yeah, exactly.
But no, I know that there is physics behind it, and that physics is held up by Bernoulli's theorem.
Yes.
Bernoulli's theorem, I'm pretty sure I'm saying that name right. So.
Yeah, that's how I said it at the center, so...
So Bernoulli's theorem says that as a fluid moves faster, as its velocity increases, the pressure of that fluid decreases. And let's just start with that as fundamental truth. As a fluid moves faster, its pressure decreases, its pressure inside itself. So, taking this to airplanes, airplane wings are designed in a way that makes air move faster over the top of them than it does over the bottom. And you can do that just by being very careful about the shape of the airplane wing. And so the air moving faster over the top of the airplane wing, because of Bernoulli's theorem, means that the pressure is also lower on top of the airplane wing, lower than the pressure on the bottom of the airplane wing. And because fluids or gas or pretty much anything in physics likes to move from high pressure to low pressure, that high pressure environment under the wing pushes up and lifts the wing and lifts the whole plane.
Yeah.
That's how planes work. It's just air moving faster in one part.
It was all these forces working together to keep it.
Yes, it's amazing. So that when you're on a plane and someone says, oh, we've reached turbulence, no, you've been in turbulent air the entire time.
Yes.
You're going through rougher, more turbulent air. This is actually something we can quantify. We can quantify how laminar versus turbulent a fluid is with a quantity known as Reynolds number, named after a scientist.
Okay.
Reynolds number tells you how laminar or turbulent the fluid is, and it is the ratio of inertial force over viscous force in the fluid. So inertial force is how hard is it to get this fluid to start and stop moving?
Okay.
High inertia means it's really hard to get it to start moving, and then once it's moving, it's hard to get it to stop.
Okay.
Whereas viscous force is kind of how thick is the fluid? How oozy is it?
Yeah, exactly.
So turbulent flows have very high Reynolds numbers because they aren't very viscous. You tend to find turbulent flows in less viscous fluids like water, whereas laminar flows have very low Reynolds numbers because you tend to find those in more viscous material.
Okay, yeah, that makes sense. A thicker substance, or what feels kind of oozy and gross. Slime.
Right.
Nickelodeon slime.
Yeah. Or oobleck, that stuff you make with cornstarch. That's just some fun fluid dynamics vocabulary for you.
Hi, it's Corinne. I want to give a quick shout out to our amazing patrons who are keeping this podcast going. Thank you to our sun-like stars, Sharn Llewellyn and Finn. Thank you to our latest Red Dwarf star, Jeremiah Franco. And thank you to our latest pre-main sequence stars, Scott Johnson, Jake Metzger, Tyler Chatt, and Dex Dog Detective. And you too can support us, hear your name on this pod, make it to our patron star chart, all by supporting us on Patreon. Find the star chart, Patreon info, and so much more. Well, not that much more, at our website, palebluepod.com.
Hello, it's Moiya with my sick voice on hand. I'm here to recommend another podcast that's part of the Multitude Collective, and it's called the Queer Movie Podcast. QMP is a queer movie watch party hosted by Rowan Ellis and Jazza John, and you can join them every other Thursday as they research and rate their way through the queer film canon one genre at a time. From rom-coms to slashers, contemporary art house cinema to black and white classics, Queer Movie Podcast is a celebration of all things gay on the silver screen. And since we just did an episode about how the whole universe is one giant big rainbow that we can't see, I feel like this is pretty appropriate. You can enjoy new episodes of Queer Movie Podcast every Thursday in your favorite podcast app or by going to queermoviepodcast.com. Fantastic SEO. I'm so jealous of them. So go check that out if you would like to hear more about queer movies every other week.
This episode is brought to you by BetterHelp. I know I feel like my best when I'm confident and have a good grip on my life, but I also know that feeling can be rare. When you're at your best, you can do great things. And sometimes life just gets you bogged down and you may feel overwhelmed or like you're not showing up in the way that you want to. Working with a therapist can help you get closer to the best version of you. Because when you feel empowered, you're more prepared to take on everything life throws at you. And therapy is helpful for so many reasons. I can't emphasize enough how much therapy has helped me. I used to describe my days like I'm feeling like I'm holding too many balloons, and if I make any movement in any direction, I might lose them all. And these days, it's so much easier to manage my anxiety, myself, my goals, just everything in my life. Therapy is helpful for learning positive coping skills, learning how to set boundaries, and so much more. And I want to emphasize it's not just for those who've experienced major trauma. Anyone can benefit from it. If you're thinking of giving therapy a try, BetterHelp is a great option. It's convenient, flexible, affordable, and entirely online. Just fill out a brief questionnaire to get matched with a licensed therapist, and you can switch therapists at any time for no additional charge. If you want to live a more empowered life, therapy can get you there. Visit betterhelp.com/palebluepod today and get 10% off your first month. That's BetterHelp, HELP.com/palebluepod.
Listening to Pale Blue Pod is a great way to learn about astronomy concepts, but it's no secret that we're not here to make you better at math. If that's the type of thing you're after, I'd like to recommend Brilliant. Brilliant is a program online and in app form for lifelong learners that replaces lecture videos with hands-on interactive lessons. You can learn about the complementary angles in a triangle by actually stretching out a triangle on your screen to see the angles change in real time. And you can learn about the center of mass in physics by trying to balance a weighted beam on your digital finger. Those are just a couple of examples. Brilliant has thousands of lessons in math, scientific thinking, and even computer algorithms, and they add new ones every single month. I think that the world really needs more people who can use knowledge and logic to reason through problems, and Brilliant is the best way to practice those skills online interactively. To get started for free, visit brilliant.org/palebluepod or click on the link in the description. The first 200 of you will get 20% off Brilliant's annual premium subscription. Again, you can join Brilliant for free at brilliant.org/palebluepod or the link in the description. And come on, have a good time getting smarter. We still have not talked about fluids in space.
Let's get there.
So I'm pretty sure, have discussed in previous episodes what the pie chart of the universe looks like. We know that most of it is dark energy, and of the matter, the stuff that uses gravity, most of that is dark or transparent matter. So what's left, the little slice of pie that's left, we call baryonic matter, regular matter that does interact with gravity and light. So you and I, Corinne, we are baryonic matter.
Yes, we are.
When astronomers took essentially like a census of all of the matter in the universe, or like all that we could measure, what they found was that 90% of the baryonic matter in the universe, the regular matter like you and me, is made up of gas of different temperatures.
Whoa.
So much of space is gas. And gas is a fluid. So there's a lot of fluid dynamics happening in space.
Okay, of course.
So we use fluid dynamics as astronomers when we are studying galaxy collisions because we want to know how all of that gas is interacting and mixing together. Or we use it when we're studying star formation because stars form from clouds of gas that contract in on themselves. So we have to know how that gas works before the star gets formed. Even internal stellar processes, because stars are collections of gas and plasma, which can flow. We use fluid dynamics to figure out what's happening inside a star. Winds in space, we have these walls of particles coming off of stars, coming off of black holes. Anything energetic enough can give off these cosmic winds. And my favorite, the thing that we talked about so often in this fluid dynamics class, was shock waves.
Ooh.
Anytime any material in space moves faster than the speed of sound, so at supersonic speeds, it generates a shock wave.
Okay, that's like the Superman animation. So he like takes off and there's like stuff, residual stuff.
Absolutely, yeah. There's that boom and like there's a pressure wave that you can study going through a sort of medium. We talked about shocks so much in the fluid dynamics class that there were 3 grad students in my cohort. We were all 3 women. I love that for us. We were all 3 queer women, and I really love that for us.
Okay. I feel like that's all of them were in that cohort.
we collected them all.
You found each other and did it.
And at the end of that class, we took shock shots of tequila.
That's so cute.
Yes, which might be why I don't remember what all of the symbols in my notes mean.
Yeah, the final.
So I mentioned before that the fluids in space can be moved by convection and magnetism. I didn't explain what that meant or how it worked, so let's get into that.
Let's get into it now.
Starting with convection. Have you heard this term convection before, Corinne?
Yes, but in terms of like a convection oven.
Yeah.
Or like something like a kitchen word.
Yeah, absolutely. I don't know what the point of a convection oven is. Like, I used to have an oven that had the different settings, and I was like, I don't know.
There's like a convection button too. I think it's kind of like it just circulates better, I want to say, but I'm probably wrong.
Okay, because their definition of convection does not match up with my physicist's understanding of convection, so I'm just very confused.
Well, if you Google it, it says conventional ovens feature heating elements on the top and bottom of the oven cavity. Convection ovens have these elements in addition to a fan that helps circulate hot air throughout the oven cavity.
Oh.
So it is what I thought.
Oh.
It's usually like a fan symbol. Also, I have the world's tiniest oven. It doesn't do anything fancy, so I'm not working with a convection oven here.
just the conventional ovens.
Yeah, very conventional.
Okay, so in space, I'm not going to touch on convection in your oven, but convection in space, or in most other circumstances, works by taking advantage of differences in density, temperature, and pressure. So imagine you have a fluid. Let's imagine you're boiling a pot of water on your stove. You have a fluid, water, and there will be bubbles in it. There will be little pockets of air or of water. There will be little water bubbles there. If you have a bubble that is less dense than the material surrounding it, it will rise.
Okay.
We are very familiar with this in other areas of life.
I'm thinking boats. Boats, buoyancy. Yeah.
Yes.
I feel like how a plane flies and how boats work are like the 2 big questions in everyone's life.
Absolutely, yes.
So we're touching on a little bit of all of it.
This is a kind of space light day. I'm talking about a lot of things here on Earth.
Yeah,
but that's fine. I think it's good to make the connection.
It's all connected.
Yes. So less dense material will rise. And the opposite is also true. If you have a packet or a bubble that is more dense than its surroundings, it will sink. And that's essentially how convection works. You find it in your everyday life when you're boiling water. Even like wind can be like a kind of convection.
Sure.
But in astronomy, we care a lot about convection in planetary atmospheres and in stars as a method of transporting heat. So when I was in high school in a physics adjacent class, I learned that there are 3 ways to transport heat from one place to another. You can do that through radiation. That means heat that can just travel through any vacuum-like medium. Like it doesn't need a physical thing to transport the heat. You can do that through conduction, which is when things physically touch each other and transfer their heat that way. Or you can do it through convection, which is very efficient in fluids.
Okay.
So different types of stars have different heat transfer methods that they will use, just radiation and convection. But it gets kind of complicated because stars have layers. They're like an onion. And if we're just paying attention, for example, to stars like the sun, their innermost layer would use one of these methods, like radiation, and then their next layer would use convection, and then the next layer after that would use radiation again. And it changes depending on the density of that part of the star. It's really complicated. And
I'm nodding. I'm like, okay.
Yeah. So all you need to know is that convection is good at transporting heat from the center of a star to the surface of that star, because at the very center, things are very hot. That's where the fusion is happening. That's where all the energy and heat is produced. So you have these little pockets, these little bubbles of star material at the center that are very hot.
Okay.
What we know about things that are very hot, if you have a high temperature, you likely have a low density.
Okay.
A high temperature, because it will expand, and you'll have the same amount of material, but in a larger space, so you will be less dense.
Okay.
So you have these less dense bubbles coming from the core of the star and rising.
Got it.
Because that's how the convection do. And then when you closer to the surface of the star, you have cooler pockets. Because they're not as close to the fusion reactor in the core of the star.
Yeah.
They get cooler, they get denser because they contract on themselves. They get denser and then they fall down. And then you get this like churning.
Oh, it's like a
mixing.
cycle. Okay.
So when you watch a pot of water boil on your stove, you're seeing that churning.
Wait, this is like a lava lamp.
Yes, it is a lava lamp.
Yeah. Wait a second. I know this.
Boats and lava lamps.
Boats and lava lamps. This is my language now.
There you go. So convection and like this focus on the temperature and density and pressure of different parts of a fluid can lead to some instabilities. And when I say instability as an astrophysicist, and maybe other areas of science use it this way too, what I mean is like a runaway effect.
Okay.
Kind of like the snowball Earth was a runaway effect where the Earth got very cold and covered in ice, and then that ice reflected a lot of the sun's heat, so the Earth got even colder, and then the whole process just got worse and worse and worse.
Okay.
That's how instabilities work for astrophysicists.
Okay.
Like once you start this process, it will just snowball or cascade or get more and more unstable. So one of these instabilities is called, they are named after scientists.
Of course.
One of these instabilities is called the Rayleigh-Taylor instability. I know that you have all seen this. This happens between fluids that have different densities. So like oil and water, when you've mixed those together and you see like the oil dripping down into the water.
Yeah.
That is a Rayleigh-Taylor instability.
Oh, okay. That's, take it back to the salad dressing. I know exactly how that one works.
Everything goes back to salad dressing. And then the other instability that you might find because of convection is the Kelvin-Helmholtz instability, which happens when there is a shear stress in a fluid. A shear stress is like when things are slipping by each other and there's a little bit of friction involved.
Okay.
So Kelvin-Helmholtz instabilities can happen through that type of stress, or it can happen when you have two fluids moving in an opposite direction.
Okay.
So actually, you usually see these instabilities happening at once, because if you imagine like a lava lamp or oil on top of water, it drips down, the water is going up. So now you have this difference in densities, but you also have the difference in direction. So you'll see these little like eddies or swirls at the interface between these two fluids.
Sure, yeah. I love that like meeting point.
Yes.
In them. I feel like that was such an experiment in elementary school of like oil and water and like dyeing it maybe a specific color to like watch it better.
Yes. So, something that I often do, and I am not condoning or encouraging the use of mind-altering substances, but if you're into that, maybe consume some mind-altering substances and then light some incense and just watch the smoke.
This is exactly it. Oh my God, watching smoke in that headspace is incredible.
Yes,
There's
especially
nothing like it.
because when I watch smoke in any headspace, but like especially that one, I am thinking about the fluid dynamics of the smoke.
That's
and I'm like,
so funny.
I'm literally sitting there going like, ooh, look at that swirly Kelvin-Helmholtz instability.
You're having a totally different time than I am. I'm looking at it and I'm like, that's magic. That right there, there's no explanation for that.
Absolutely none.
And now I'll think of this.
Good. Please do. Anyone, if you're watching smoke or if you're watching any sort of interaction between fluids, and like, yes, the smoke is one fluid, the air that the smoke is moving through is the other fluid involved.
It's so interesting to think of smoke or gas as a fluid because I so associate the word fluid with liquid.
I know. Most people do.
It explains so much of like smoke's movement or things like that, whereas it just feels like a liquid in the air or like it's moving in that river kind of way.
Exactly. Yeah, it's a vertical river.
Yeah, exactly.
Moving through the air. Okay, so that's convection. Those are two of the major instabilities that we'll see in fluids due to convection. But I also mentioned magnetism. There are magnetic energies and magnetic charges everywhere in the universe. Magnetic energy or magnetic fields happen because of the motion of charged particles. So here on Earth, we have a magnetic field because of the movement of our liquid iron core in the center of our planet.
Okay.
That creates a magnetic field. Out in space, you can have stars with electric charges. You can have individual particles with electric charges. You can have whole columns or jets of material with electric charges. So there's a lot of magnetism out in space, and the shape of that magnetic field, we will often draw lines indicating like the motion of the magnetic field. That shape depends on how those charged particles are moving around.
Okay.
And because those particles often aren't moving on perfectly straight lines, it's kind of chaotic motion because those particles are moving according to fluid dynamics and then influencing the magnetic field line shape, which then influences the fluid dynamics. It's all...
It creates that cycle again.
Yes, exactly. This is why we have a feedback loop. But what I'm trying to say here is that because the charged particles themselves are moving in a kind of wild way, the shapes of these magnetic fields can also be kind of wild.
I buy that.
So now we're going to start talking about plasma.
Okay.
Which can be a fluid, often is a fluid.
And is this anything like blood plasma?
No.
Okay. All right.
I think
ask.
that is that's a totally different word. I don't know what blood plasma is, but it is not plasma in the way that astronomers talk about, because a plasma for us is a very hot, electrically charged substance.
Yeah, my blood can't be that hot.
No, it is not. Your blood is not millions of degrees.
Not me. Maybe somebody.
Maybe if we were a cold-blooded species and we went and stood right by the sun.
Yeah.
But no, our blood is not astrophysical plasma.
Got it.
But we do find astrophysical plasmas out in space. And so these plasmas or other charged fluids, like it has to reach a level of electric charge to be considered a plasma. So any fluid with an electric charge can follow these magnetic field lines, but those lines aren't always stable and their shapes are ridiculous. So there are a couple of instabilities that we get because of magnetic field lines out in space. And unlike, I'm getting giddy, unlike the instabilities for convection, which are named after scientists, these ones apparently just have stupid names. Just names.
A totally different group of scientists behind this one who are naming it what they wanted.
Exactly. They were like, I don't need this instability named after myself.
This doesn't need to be my name. Exactly.
I'm going to give it a name that I think is demonstrative or illustrative of what it actually is. But it's not. It's not, friends. So,
that's so funny.
One of these instabilities is called the sausage instability.
That's so funny. I'm Googling it just to confirm if it looks like a sausage or not. Kind of does.
Kind of does, yeah.
Kind of does.
So imagine you have this column of plasma. Actually, I will give you an example of where we might find this so I can talk about specifics. One place that we might expect to find plasma, like a stream of plasma out in space, is around a black hole.
Okay.
So if you have a powerful enough black hole, it's massive enough, it's accumulating enough material, there's enough energy there, what you'll see are these two giant bright jets that shoot out of the black hole, basically going towards the North Pole and towards the South Pole of the black hole.
Okay.
Those jets are made from material that gathers around the black hole that gets shot out away from it. For a long time, it was a big mystery how that happened. Now we're starting to learn more about it, and we think it might have to do with these magnetic field lines. So it's very exciting. But picture one of those jets coming off of a black hole.
This is a fun thing to Google image, too.
Oh, yeah, they're gorgeous. Okay, imagine you have these jets coming off of the black hole, and they are columns. They're like cylinders. The magnetic field lines can move around them, like spiral around these jets. So you essentially end up with rings of magnetic field line going around the jet. Those rings can contract. Like if you build up enough magnetic energy, you'll get a lot of magnetic pressure in a certain point, and the ring will contract until it like pinches off.
Okay.
Pinches off the jet coming from the black hole.
Is that a sausage? Are we still talking sausage?
Well, that's why it's called a sausage, because it pinches off on either end. And I guess they didn't want to call it like the poop instability.
Yeah,
so
sausage links instead.
sausage links. Yeah, it looks like links of sausage. And that's when the energy pinches the whole column. But you can also get something where the magnetic energy and the magnetic pressure build up at a certain point on one side of the column. That pressure will push against the column, making it bend, which then invites more magnetic energy and pressure because you're concentrating the magnetic field lines, so it bends even more. And that cycle just continues until this jet snaps in half, basically.
Okay.
Like snaps to the side. And that instability is called the kink instability. For some reason. Why do we do this to ourselves?
I get it. I do get it. It's good to keep it fun.
Yeah. Yeah.
It feels like a dented can is kind of like how I'm picturing something like this.
Yes. That's a good image.
But I guess that's definitely a worse name than the kink instability.
Yeah, I remember being in fluid dynamics class, and when our professor said the words kink instability,
I'm sure you lost it, or I hope.
We kept our cool, but the two other people in my cohort and we all made eye contact around the room. And there was that moment where we were like, okay, we can't react now, but after
I'll talk
class,
to you later.
We're going to laugh our asses off. And we did.
That's really special.
Yeah. So yeah, that is fluid dynamics. Do you have any questions about fluids or their dynamics or this class?
We talked about smoke, but I'm curious what like the most common fluids in this kind of context are that I interact with probably. I guess smoke, steam?
Dude, air. You breathe a fluid all the time.
That's crazy.
Water that you drink. Maybe we should play a little game of, is it a fluid? What is a fluid?
All right. Should I list things or should you?
We can alternate.
Yeah. Well, water's blowing my mind. Well, not water. Air is blowing my mind.
Mm-hmm. Yeah, so air is definitely a fluid. What about, like, oobleck? I'll just go straight to the hard one. Ooh. That mixture of cornstarch and water. Is that a fluid?
Well, I feel like I want to say yes. But so I interacted with oobleck last summer when I was running a camp for kids, and we were just like, it was raining every day, and I was like, great, you can go make oobleck in the corner again.
Nice.
So they made that a lot. It was a really interesting thing. Like, that's what they find so interesting about it, of like, it's so hard to interact with something like that in a day-to-day basis, because it's not quite slime, and it's not quite water.
Right. It's something in between. We actually call it a non-Newtonian fluid in science, because it doesn't adhere to the typical rules of Newtonian dynamics.
Right.
So this is a tricky one. Maybe I shouldn't ask
what is
this
it?
right away. Well, okay, so the thing about oobleck is that its state varies based on how much pressure you apply to it.
Yes. Yeah.
So if you hit it really hard, it becomes a solid because you're applying a lot of pressure and it contracts, it becomes a solid. But if you don't apply much pressure, if you just like slowly put your hand into it, then it acts more like a fluid.
Yeah, yeah. And that's what's so cool about it. Also, isn't it crazy easy to make? It's just like cornstarch and something else.
It's just cornstarch and water.
Oh my God, everyone go make this.
Go make it. So oobleck, we have decided, is sometimes a fluid.
Oh, okay. So things can sometimes be it depending on the pressure and... Okay. Interesting. Well, I can't think of another thing I've ever interacted with.
What about people, Corinne? Yeah, what about people? Are we fluid?
That's crazy. I like to think I'm always changing.
Yeah. Well, there are definitely aspects of myself that are always changing, you know, like gender, sexuality. Some people are very fluid in that aspect.
I'm always fluid.
And we certainly have many fluids in us as humans.
Well, we even have plasma, if you follow my school of thought. I feel like maybe we can be like oobleck.
This is interesting because when you start thinking larger than the scale of individual objects and put them together, like cars, an individual car is not a fluid. But if you take a bunch of cars,
the traffic jam before. Okay.
Yeah, like because you can talk about the flow of traffic.
Yeah.
And so as a group, they are a fluid. Humans, when you get us into groups, we can move as a fluid.
Like crossing the street in New York City, it can feel like that. Yeah.
Exactly. Or even, this is like a terrible tragedy, but when crowds swarm, like when you get a big crowd of people and it starts to move as one, that is fluid motion. Like you can really see it at big concerts or something.
Yes, totally. I went to a very crowded high school. There were 4,000 kids in this building. There's 1,000 kids per grade. I know you had a very starkly different experience, but that's what's making me think of. There were a series of classes I had where it was like, there's no way I'm going to get to my next class in time because the bell rings, everyone floods out, and then we're all moving through this hallway. Yeah, exactly. We're moving through this hallway, and I remember it felt so crowded. I was like, I am sandwiched between bodies right now in a way that I could lift my legs up and I would still be carried forward in this group.
Oh my God. Terrifying. But yeah, that's a fluid.
And me, the good student is just sweating that I'm going to be late to this class.
I know the feeling. I also hate being late, especially to class.
I know. I want to settle in.
You want to be there. You want to calm down. You want to be able to wipe all the sweat off.
Yeah, I got to
before your crush comes into the room.
Exactly. That hallway was so crowded. Speaking of crush, I had a friend who had large curly hair and she wore it down often, and a boy and his girlfriend were making out in the hallway and he reached for his girlfriend's head to touch her hair, and he fully put his hair in hers not knowing, and she was just like, what do I do now?
Oh no.
Do I sit? I think she kind of because we're just all moving in a way, it was she got out of it, but it was definitely this is what happens.
That's unfortunate for multiple reasons.
It was so gross.
Don't touch my hair, but also don't involve me in your kissing shenanigans unless I want to be.
Yeah, exactly. It was clearly okay, we should be staggering the dismissal of classes. This needs to be different.
You should go back to your high school and
I'm gonna give them this one idea.
You can bring up laminar and turbulent flow.
Yes.
Be like,
Look, I went off, I graduated, I explored the world, and look at all I learned. I think you can apply it.
No, that actually is a really good example of laminar versus turbulent flow, because when you have all of these students packed in the hallway, they're going in different directions. That's very turbulent.
Yeah.
If you had a less dense medium, then people would be more able to move in parallel directions.
Exactly.
So I think the rule here, or the lesson here, is that most things can be a fluid, especially if you put them in a big enough group.
Yeah, that's really cool to think about. I love that.
Cool. Hey, Corinne, my tummy is growling. I really want one of those corn dogs.
I am dying to eat something. Maybe a big lemonade, too.
Ooh, yeah, I love those. Maybe a fried Oreo?
Oh, yeah. We can get that with the pickles.
Okay. So we're going to go and eat all of the unhealthy for our bodies, but very healthy for our souls, carnival food. And whether you are eating a corn dog or not, remember, both you and that corn dog are space.
You are space. Bye.
Bye. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.